I'm actually at home, so it was being just heading downstairs.
Very good. Okay, so
should I start?
Yes.
Sharing the screen?
Right. Well, let me just introduce what this is for a second. So,
Marque, já está ao vivo.
Ok. Bem-vindos a todos para a defesa da qualificação de doutorado do Gabriel Freitas Silva, aluno meu no CBPF. Eu vou mudar para o inglês porque um membro da banca externo da banca ela não entende português. So welcome everyone to the defense of the qualification of the PhD of Gabriel Freitas Silva, student of mine in CBPF. The members of the board of the examining board is Professor Adrian Otterwill from University College Dublin in Ireland, and the CBPF internal examiner is Tiago Alves Silva. So the idea is that Gabriel presents, gives a presentation for about 30-40 minutes, and then we'll move on to the questions by the examining board, starting with the external examiner. And for a while they'll be asking questions and Gabriel will be answering. I'll try to not really take part in that. And afterwards, the two examiners will separately and privately write a report on the defense and the thesis so far by Gabriel. Anybody has any questions?
No.
Okay, so I think you can start whenever you want, Gabriel.
Okay, so let me share the screen. Do you see the presentation?
Yeah.
Yeah.
Okay, so thank you, Mark. Thank you to the examiners. So the title of my project is Renormalization in Quantum Field Theory in Curved Spacetimes via mode decomposition of the Feynman Green function. And the outline of this presentation is that first I'm going to introduce the general theory of normalization in curved spacetime, specifically the point splitting method. Then I will describe the method that we are proposing, and in particular apply it to the renormalization of the expectation value of phi squared for a scalar field, a massless scalar field in Rising-Nordstrom spacetime, then describe the actual numerical implementation of this calculation, and in the end, the conclusion of all of that. Okay, so first of all, let me motivate what, let me describe the motivation for this project, which is in quantum field theory in curved spacetime, operators which are quadratic in the field, so for example, phi squared for a scalar field, or the stress energy tensor, are important quantities. However, their expectation value must be renormalized. And now, of course, these renormalization techniques are known for a long time, but the practical implementations usually rely on Euclideanization of the spacetime. And that's very useful in many spacetimes, for example, Schwarzschild, Rising-Nordstrom, and so on. But it's not possible in general. Most importantly, it's not possible in Kerr spacetime, which is of astrophysical and theoretical importance. So the motivation of this project is to propose a new method which works in the Lorentzian sector, not in the Euclidean sector, so that it can be used, for example, in Kerr spacetime. Okay, so let me first describe the point splitting procedure, which is used to regularize. It's the typical regularization procedure in curved spacetimes. So the idea is to express a quadratic operator, for example, phi squared, as a limit of a product of two operators on different spacetime points. So for example, phi squared can be expressed as a product of phi at point x and phi at point x primed, and then take the limit as x primed goes to x. Now, of course, that formally, that means that phi squared can be expressed as the coincidence limit of the Feynman function, or actually the imaginary part of the Feynman function. And the stress energy tensor can be expressed as the coincidence limit of some differential operator acting on the Feynman function. This differential operator actually acts both on x and on x primed. Now, renormalization proper, this is a formal expression, of course, because this limit is not well defined. The limit is actually infinite. And so renormalization proper is performed by subtracting a counter term from the Feynman function. And now the question, a counter term which contains all of the singularity structures so that the limit is well defined after the subtraction. And of course, now the question is how to construct such counter term. There are many proposals in the literature. In this project, we use Hadamard regularization, which the idea of Hadamard regularization is that the green function equation admits local solutions of the Hadamard form. So solutions of this type, where sigma is the world function, that is the 1/2 of the square of the geodesic distance between x and x primed, and u, v, and w are regular biscalars. So they depend both on x and x primed, but they are regular. So one can see that the singularity structures is contained in the first and second terms in this 1/sigma and the logarithm of sigma. U and v are purely geometrical. They do not depend on the quantum state, but W depends on the boundary condition. So the quantum state is described by W essentially. So the idea of Hadamard regularization is to take the singular part of this Hadamard form, so these first two terms, as the counter term to be subtracted from the Feynman function, since they contain the singularity structure of the Feynman function. Okay, so we are going to use this expression, the singular part of the Hadamard form, as the counter term to be subtracted. However, the problem is that even after you have an expression for the counter term, a practical implementation of the point splitting procedure is difficult to implement, because that happens because the Feynman function is usually expressed in terms of a mode sum of modes which can only be expressed numerically, while the counter term, as we saw, is expressed as an expansion in terms of sigma, which is a geometrical quantity. So it's not obvious how to perform the subtraction and take the coincidence limit. Typical implementations of this procedure, numerical implementations of this procedure, follow the work of Howard and Candelas, but they all rely on Euclideanization of the spacetime. And as I explained before, Euclideanization is not possible in general. Most importantly, it's not possible in Kerr spacetime. So it has always been important to devise a method which does not require Euclideanization. And more recently, there have been advances in that area. Specifically, a method called programmatic mode sum has been proposed by Levy and Ori in 2015, which in spirit is very similar to the Candelas and Howard's method, but it does not require Euclideanization. And their method has been used to calculate the renormalized expectation value of the stress energy tensor in both the exterior and the interior region of Kerr spacetime, which is a major result. And also, a method has been proposed by Taylor and Breen, which consists in splitting between x and x primed in multiple directions and then decomposing the counterterms using what they call extended coordinates. However, Taylor and Brin's method require regularization. The method that we are proposing in here is similar to Taylor and Brin's method, but we are working in the Lorentzian sector. So, okay, so let me describe our proposal in a summary of our proposal. The idea is to separate x and x prime in multiple directions, then expand the counterterm for a small coordinate separation. Then each term in this expansion is decomposed into L and omega modes. Then each mode is subtracted from the unnormalized Feynman group function, from each mode of the unnormalized Feynman group function, mode by mode. And then after the subtraction, the coincidence limit can be taken and the mode sum can be performed, given a finite value. Let me describe this in more detail. I'm going to describe this in the specific case of a spherical symmetrical spacetime. But in general, this method should work in general, not only for a spherical symmetrical spacetime. Okay, so the idea is that the Feynman group function is expressed as a mode sum, a sum over L and omega. So we want to express the counterterms as a mode sum similar to this. We first expand the counterterm for a small coordinate separation. That's going to give something like this. A logarithmic part which comes from the tail part of the Hadamard form, polynomial part which comes from the direct part of the Hadamard form, and some independent term, where each one of these terms has a different order in the coordinate separation. So Gn has order delta n, where delta is the order of the coordinate separation. Then each one of the, we have these logarithmic terms in here, but we are actually going to ignore them from now on because we don't need them for the calculations that we're going to do. But in the general idea of the method, these logarithmic terms are in here. Now we decompose each one of these terms into L and omega modes by calculating this. And then after decomposing into L omega modes, the result for the renormalized value of phi squared is expressed as the mode sum of this subtraction. We can express the mode sum both via L sum first or via the omega integral first. The difference being the independent term that appears here in front, outside the mode sum. This term depends on the order in which you take the mode sum. But a strength of our methods that we can perform the integral, the mode sum in whichever order we want to. And in fact, in our numerical implementation, we calculated the L sum first in the interior of Rising-Nordstrom spacetime, while in the exterior region, we performed the omega integral first. Okay, so now let me describe the actual application of this method to Rising-Nordstrom spacetime, specifically to calculation of the renormalized value of phi squared in both the exterior and in the interior region of Rising-Nordstrom for a massless scalar field. And as I said, we're going to separate the interior region and the exterior region because the calculations are going to be a bit different in these two regions. But first of all, we need to express the unrenormalized Feynman group function in terms of the modes of the modes of the field, and so the field equation for a scalar field in Rising-Nordstrom spacetime can be separated using the spherical symmetry of the space-time. The field equation can be separated using spherical harmonics, which leads to a radial equation, the Regge-Wheeler equation, which is a Schwarzschild-like equation with this kind of spherical of effective potential. Now, of course, we have to define boundary conditions on these modes in order to get a complete set of mode solutions to this equation. And this complete set of mode solutions will be different in the exterior and the interior region. In the exterior region, one typically defines these ingoing and outgoing solutions, which are defined by their asymptotic behavior on the past null infinity and past event horizon, like this. And then the unnormalized modes of the Feynman-Green function, specifically the Hartle-Hawking state, because in the exterior region, we're going to calculate phi squared in the Hartle-Hawking state, can be expressed in terms of these ingoing and outgoing solutions like this. In the interior region, on the other hand, it has been shown by Lanier and collaborators in 2018 that this set of mode solutions, which are only defined by their asymptotic behavior on the event horizon, form a complete set by its own. And then the Feynman-Green function in the unrule state, because we're going to calculate phi squared in the unrule state in the interior region, can be expressed like this. This is for the interior region of Royce-Nordstrom. Now we move to the counter term. As I explained before, we want to first expand the counter term for small coordinate separation and then decompose it in L omega modes. And we've shown that that the counter term can be expanded like this. In particular, we re-express this expansion in terms of this kind of variable s squared, which is similar to one of the extended coordinates defined in Taylor and Bring's method. It's not exactly the same, but it's similar. And we found an expansion expressed like this to be particularly useful in our case. These coefficients of the expansion are depend only on R, and we've calculated them up to order n equals to 2. So the first 5 leading orders have been calculated. And as I said, the logarithmic terms are actually going to be ignored in this calculation because we don't need them for the calculation of phi squared. Oh, right, and this expansion is general for general coordinate separation, but specifically in the case for r equals to r primed, this expansion simplifies a lot. And for the calculation of phi squared, we only need r equals to r primed. So this scenario simplifies greatly in our case. Okay, now we move on to decompose each one of the terms of that expansion into L omega modes. The calculation is quite lengthy, but it's described in detail in the text of the qualification. The result is this ugly expression, which again, in here, it is written for general coordinate separation, but specifically in the case for r equals to r primed, it simplifies greatly. And we only need, for the calculation of phi squared in the exterior region of Royce-Nordstrom, we only need this expression for r equals to r primed and only for n equals to 0 and n equals to -2. And in that case, the expression simplifies to this, G omega -2 and G omega 0. As you can see, these modes are expressed in terms of spherical Bessel functions. But in the interior region, we found that it's best to re-express these modes in terms of modified Bessel functions. Mathematically, it's equivalent. It's just a matter of convenience. But in the interior region, we re-express in terms of modified Bessel functions like this. Okay. Now, of course, since we are going to subtract GL omega from FL omega in order to get a finite result, we expect that the large omega behavior of GL omega should cancel the large omega, the divergent part at least, of the large omega behavior of FL omega, and similarly for the large L behavior of FL omega, it should be canceled by the large L behavior of GL omega. And since we are going to perform the mode sum via omega integral first in the exterior region, we are going to explore the large omega behavior of GL omega n in the exterior region. And in the interior region, since we performed the L sum first, we're going to explore the large L behavior in the interior region in order to check whether GL omega does cancel the divergent behavior of FL omega in each one of those regions. So in the exterior region, we can obtain the large omega behavior of GL omega via a closed form expression, which is rather interesting because the spherical Bessel functions actually can be expressed as a finite sum of elementary functions that allows us to re-express GL omega in the exterior region as this exact expression, closed form expression. As you can see, there are oscillatory terms. Xi is proportional to omega, so this term oscillates with omega, while these terms are non-oscillatory. And this kind of expression automatically gives the large omega behavior of GL omega in the exterior region. And note that it's not an asymptotic expansion, it's an exact closed form expression. But we saw that the non-oscillatory terms, which are these ones, do cancel the large omega behavior of FL omega. To be more specific, we saw that GL omega minus 2, the leading order of GL omega minus 2, which is of order 1 over omega, cancels the 1 over omega term in the large omega expansion of FL omega. The next to leading order, which is 1 over omega cubed, is present both in GL omega minus 2 and GL omega 0, and the sum of them cancel the 1 over omega cubed term in FL omega. And we believe that that happens up to arbitrary order, so that, for example, the 1 over omega to the 5th term in FL omega would be canceled by the sum of GL omega minus 2, GL omega 0, and GL omega 2. Okay. Now, in the interior region, as I said, we are going to explore the large L asymptotics because we performed the L sum first. We didn't find a closed form expression in the interior region, but we can of course calculate the asymptotic expansion of GL omega in the interior region. That gives an asymptotic expansion like this, where these coefficients A, B1, B2, and so on can be calculated analytically. And we compare this asymptotic expansion with an asymptotic expansion of FL omega, and we see again that GL omega minus 2 cancels the leading order of FL omega, and GL omega minus 2 plus GL omega 0 cancel the next to leading order of FL omega. And again, we expect that this happens up to arbitrary order. Okay, so now let me describe the numerical implementation of all of that. The numerical implementation is actually a bit more difficult in the exterior region. where, as I said before, we perform the omega integral first, so that the mode sum can be expressed like this. Now the problem is, as I said, GL omega minus the large omega behavior of GL omega minus 2 has an oscillatory part. And as you calculate the integral up to infinity, this oscillatory part brings problems to the numerical computation of this integral. So our idea was to separate this integral into 4 parts in such a way that the third and fourth parts can be calculated analytically, and these 2 first parts are calculated numerically. But the oscillatory behavior of GL omega minus 2 only appears in the numerical part. It only appears in this first integral, which is only performed for small values of omega. So these oscillations are not problematic in here. The second integral does not have any kind of oscillations, and the third and fourth integrals do have oscillations, but they are performed analytically. Now, after performing the omega integral like this, the L sum is much more straightforward, and the result of this mode sum is given in this plot, which agrees very well with previous literature up to the numerical error. Okay, and then in the interior region, the implementation is more straightforward because there are no oscillations in L or in omega, so we can just perform the L sum and then the omega integral straightforwardly. And the result is given in here for a black hole with charge of 0.8 and n equals to 1, and mass equals to 1. And again, this result agrees with previous literature up to the numerical error. Okay, very well. So that's all. We've proposed a new method, a new renormalization method, which in principle does not require Euclideanization, so can be used in more general spacetimes. We applied this method to the calculation of phi squared in Rice-Reynolds, in the exterior and interior region of Rice-Nordstrom for a massless scalar field, and the results agree with previous literature. And for the future, we intend to use what we have done so far in order to calculate the normalized value of the stress energy tensor in Rice-Nordstrom spacetime. We believe that we already have all the ingredients to do that. Of course, computationally, it's difficult, but we already have all the ingredients for that. And in the longer term, far more into the future, we expect to use this method to calculate the R set in Kerr spacetime. So that's all. Thank you.
Thank you, Gabriel. So now we'll move on to the question session by the examining board. So I would like to thank the 2 members of the examining board, Adrian Ottewell from Dublin and Tiao Alves from CBPF. Just to remind the 2 examiners, or to clarify, that this is not the final thesis of the final defense of the thesis, it's the qualification. So, typically there is also, it's not just questions, but if you have any suggestions about, calculations and future, any suggestions you might have, they're more than welcome as well. So as is tradition, we'll start with the furthest member of the examining board, the furthest from CBPF. So that's Professor Adrian Ottewell from Dublin. Adrian, whenever you wish.
Thanks so much indeed. At some stage, we might go through the thesis page by page, but let me first just start with a few general questions, and maybe this actually alludes a little bit to what Mark was suggesting here. So I was a little bit surprised when I came to see your examples, and I'll sort of go through a few reasons why. So let me start with the first one. It seemed to me that the major advantage of your method of working in the Lorentzian is you didn't need to Euclideanize. So in that case, you could have considered a thermal state with an arbitrary temperature, or even zero temperature, include the Bowler vacuum. So I wondered why you chose, or was there a particular reason that you only looked at the Hartle-Hawking state outside? Could you not have taken a general temperature Feynman function and worked throughout with it, and then got at the same time both been able to compare to the known Hartle-Hawking result, but also to generate original results at the same time? So I don't know if you have a comment about that.
No, so it was for no particular reason. I agree that we could have considered a general thermal state. So there's no particular reason. In the interior region, we chose Unruh for its physical relevance, of course. In the exterior region, we just chose to perform the calculations in Hartle-Hawking state first, and we never moved into other states. But I agree that this calculation surely could be performed for our general thermal state.
I think it would be very interesting to do, because although we know that Bowler is unphysical for a black hole spacetime, it still naturally describes what's going on outside a static star. And so if you have some sort of exotic compact object, then the Bowler state is the natural one in which to work. I mean, I think my other suggestion would have been that the long-term goal of this is surely to do things in Kerr.
Yeah.
In Kerr, we know we don't have a Bowler state or a Hartle-Hawking state, yes. And therefore we can calculate phi squared differences and stress tensor differences relative to any given fiducial state. But in that case, the only one that we have to play with is the Unruh state. So I might have been tempted also, when you were doing the calculation outside, to also just go through and calculate directly phi squared in the Unruh state.
Yeah, sure. I agree.
I'm not sure if that exists in the literature. I think I've done T mu nu, but I'm not sure I know where phi squared Unruh exists. It might be back in the original papers of Fawcett or Howard, but I think that would be interesting.
Okay. Yeah, I agree.
Okay. The next, again, in the sense of a comment, but also maybe you've done something since. You seem to me to choose examples that only tested half of your scheme. In other words, you deliberately only did cases where there was no tail, at least to this order. So because you're massless, because you're Ricci flat, yeah. V is 0 to sort of high enough order that you don't see it in phi squared. Now, I know from talking to Taylor and Breen that they actually find the massive calculation more complicated, and they need to take more modes. I don't know, have you done any experimentation to know whether those logarithmic terms would create?
So this was deliberate, actually, as you said, because the reasons that we haven't finished the calculation of how to deal with the logarithmic terms yet. So I do intend to work on this. I think that this is something that's in my plans to do until the end of this PhD project, but it's not finished yet.
Okay. So do you think you'll get similar expressions and you'll be able to relate them?
Yeah.
In much the way that you did for the direct?
I think so,
terms?
Yes.
Yeah. Okay. Very good. So a couple more questions. So your G0 looks to me very much like the green function for flat space in spherical harmonic coordinates. So you have the J regular, the origin, and the Hankel representing outgoing waves. I don't, what that made me think. I do you know the work by Parker and maybe it's Birrell and Parker, I think, of doing curved space momentum space calculations. So what they do is they take a tangent space, and what they then do is to introduce Cartesian coordinates in the tangent space and take sort of plane wave decompositions in tangent space and work from there. It seemed to me that your calculation might very naturally reflect working in momentum space, but then as to be very natural, taking something which is sort of spherically symmetric decomposition of the delta function and expanding things out. Have you come across that paper? Is this anything you?
No, I don't know this paper, but I agree with you that it is striking the similarity of having spherical Basel functions and so on. And in fact, we have already used this method to calculate phi squared in Bertolini-Robinson spacetime. Well, I did that in my master's, and we also had a similar structure of spherical Basel functions in the modes. So I don't have a good physical explanation for that, but it seems to be something that appears in many cases.
Mm-hmm. Mm-hmm. Okay, interesting. So you talked about that calculation. Have you actually done the calculation of phi squared in flat space through this method?
Yes,
for a massive field.
Yes, we did. In my master's, we did that.
Okay, so in that case, you do have the logarithms, but they cancel. Is that?
No, because in flat space time, V is 0, right? So.
Well, it would be m squared. M squared.
Oh no,
I think,
we only did that for a massless field. Yeah.
Okay. Because again, it might be interesting to look back, because again, just from interaction with Taylor and Breen, I know that when they applied their method to a massive field in flat space, they ran into issues of infrared divergences.
Okay.
And just some of your expressions look to me as though they would suffer from the same issue, because obviously your integrands are going down to omega equals 0, and you have 1 over omega terms in there. You've been handling the ultraviolet divergences by your high omega expansion. Yeah. But I wonder if there's a danger of letting infrared divergences sneak in at the other end of the integral.
This is a good question, because actually what we see, as you say, the 1 over omega cancels the ultraviolet divergences, but introduces an infrared divergence. And at least in this case, in the massless case, this infrared divergence that is introduced by 1 over omega is canceled by the oscillatory terms.
Okay.
The oscillatory terms.
So you can do that explicitly.
Yes.
Okay.
We can.
And I guess with the Taylor-Breen scheme, whether there are oscillatory terms in omega, are they?
So since they are in the Euclidean sector, they don't have omega, right? They have a discrete sum over n.
Yeah, that's right. I'm wondering whether it's an advantage of your method that you can see how the approach to omega equals 0 goes, whereas they have, as you say, the discrete.
Yes. We can see analytically how these infrared divergences are cancelled by the oscillatory terms. Yes.
Okay, I think that would be interesting. If I can move on a little bit, and I say these are still general questions, and then maybe we can go through later some of the more specific things in the thesis. In your thesis and in the presentation there now, you made the comment that GL omega of n, that expression is exact. Something that slightly concerns me is, suppose I introduce a mirror into my space-time at m is 100.
Mm-hmm.
You're going to be doing the calculation at m equals 10. All of your expansions seem to me to be very high frequency expansions. They're expansions in 1 over omega, or 1 over xi, by the time you've rescaled. How are they going to sense the boundary? I mean, what I strongly suspect, because I know this is what happens in the proper time formalism, is that you may have captured all of the 1 over xi behavior accurately, but there are actually terms in there that go like e to the minus alpha squared over xi. So they go to 0 faster than any power of xi. So although it might look exact, in fact, it's asymptotic, because in a sense it can't be, well, I'm struggling to understand how it can be exact, because it needs to sort of have a reach all the way out to very large distance.
That's a good point, but now I wonder if, because what I haven't said in the presentation is that these oscillatory terms also contain a part which grows with omega, and we have to deal with these terms separately. We have to take we calculate these integrals analytically by performing by introducing a regularization factor.
Okay.
So
is that along the lines of the Ori approach in terms of oscillation cancellation, would you say, or?
Not in the lines of Ori's approach. It's more standard. We just consider that this is the integral over omega of this is a distribution. Essentially, that gives a PV of 1 over something that depends on R, essentially. So, so I wonder if this could capture this.
It might be interesting. I mean, it would be a very straightforward calculation. I would have thought to have put a boundary outside your point. So now your spherical Bessel function is, or spherical Hankel function is modified by containing a certain amount of J, essentially, so that it vanishes at that boundary, and then see how would your calculation go through. Can you see it coming in some way? And you may then be able to come back to me and say, no, there absolutely, in the infinite case, is no exponentially small correction. But it's something that, I mean, even if you do a calculation like this in flat space with a boundary, then you can do exactly the same calculation of the Fourier decomposition in just sort of an ordinary sense, and you'll see that what I think is equivalent to these terms are present. But if you stick a boundary in, you have the exponentially suppressed terms as well. Okay, you mentioned the oscillatory parts there and the large omega. One thing that worries me, and this is just sort of looking for feedback, because I know this is something you're now going forward to do. Obviously, when you come to do the stress tensor, you're going to have 2 additional derivatives, which are going to bring down 2 powers, loosely speaking, 2 powers of omega. So any ultraviolet oscillations that you still, or that were there in phi squared, are going to be omega squared as bad when you go to stress tensor.
This is something that I have already thought about, but I think that we can deal with that. I think that we'll be able to deal with that. But that is something that is in my radar the calculation of the R set.
Okay, so is that using the same techniques, so sort of distribution theory techniques?
Yeah, exactly.
Okay. That's interesting. Okay, so again, going forwards, you were very optimistic about extending this to Kerr.
Yeah.
Yet one of the first steps of your calculation was to use the summation formula for spherical harmonics. Now, of course, as soon as you go to Kerr, you have no such calculation. So I can see that you can expand the 2-point function, but I wonder, do you see at this stage in the project, and I appreciate its early days, do you see the way that you're going to overcome that obstacle?
Yeah, so I expect that in Kerr, first of all, we won't be able to use angular separation like gamma, like we used, as you say, because we can't use the spherical harmonics addition theorem. So first of all, we'll have 4 variables instead of 3. We won't be able to perform our expansions in terms of just S, tau, and delta R. We will also need a 4th variable. So of course, we can always separate the field equation using spheroidal harmonics, right? And then re-express the spheroidal harmonics as an expansion of spherical harmonics. So this is something that I think that we should be able to do. And for the actual expansion of the counterterm, since we won't be able to use a variable like S squared, which was very specific to Schwarzschild because it uses the spherical symmetry of the spacetime, I wonder if we could use variables at least similar to what has been proposed in self-force calculations, the W1, W2, like in a Heffernan's paper on the self-force in Kerr. So I wonder if those variables would be useful in our expansions as well, because they would change the trigonometric expansions of delta theta and delta phi into algebraic expressions. So maybe that would be useful.
Have you tried to do that yet?
No. These are just expectations. I haven't tried anything in Kerr yet.
Okay. Very, and so you think you're going to try and do the expansion with the 4 points separated? Would you then, as you said here, and as Taylor and Breen say, the expressions are very much easier when you take delta R to 0 at least. Do you think there's at least a possibility of doing that and getting useful results for?
Yeah. So I think that we actually don't need to take R different from R prime, because of course, whenever you have derivatives with respect to R prime, you can change them for derivatives with respect to R using bivector parallel transport. So you don't need to have expressions with R different from R primed, but I intend at least to perform the calculations with R different from R primed, unless it gets too complicated.
Mm-hmm. Mm-hmm. And so can I just ask, in terms of your plans going forward, what directions are you going to go? Are you going to go stress tensor in static spacetimes first, and then phi squared in Kerr, or the other way around? What is your plan for the future?
Yeah, exactly. My plan is to first go to R set in Rice and Nordstrom, and then phi squared in care. That's the idea.
Okay. Very good. Thank you very much. Let me share.
Okay, thank you.
Share the screen, and then I might come back to one or two comments for explicit equations.
So should I stop sharing?
Not necessarily, Gabriel. Not necessarily. He was referring to share his time with me.
Oh, okay.
So thank you very much, Adrian, for your participation as one of the world experts in the field, and not just for the questions, but for the suggestions and insight as well. And now we move on to Tiao, the internal examiner from CBPF. Tiao, whenever you wish.
Oh, thank you very much, Gabriel and Mark, for inviting me to this board. It has been a great pleasure for me to finally consider something which is not in flat space concerning renormalization. All my life, renormalization was something for me to be done in flat space. And I am aware that in curved space, renormalization has several difficult issues that must be addressed. And I learned a lot reading your project. And even before reading your project, we have talked when you were my student in courses at CBPF, and you have briefly talked to me about your project. And it was always very interesting to hear from you about this renormalization which you performed. So this is our previous warning that I'm not an expert in the field, and so this is acceptable that I formulate trivial questions or things like this, and say some bullshit in the middle. So don't be ashamed. And first of all, I would like to ask you about something you say in the project. You do not have to share the screen with the project, but you find it immediately. One of your first equations in your second chapter refers to decomposition of the stress energy tensor as G mu nu, D mu nu times GF. Mm-hmm. And you use this structure for T mu nu to define the T mu nu renormalized from the definition of phi square renormalized, because you simply subtract GS, which is you call a counter term from GF, and apply the same structure to define T mu nu. This is okay as long as you are dealing with a scalar field minimally coupled to gravitation. Mm-hmm. But I have some doubts if this could work if you have nonlinear couplings for the scalar field. For example, if this scalar field could have a phi 4 term in its Lagrangian, for example. What do you say about this? I know that probably it makes no sense to put some self-interacting term in the scalar field Lagrangian, but let's suppose for some moments that this is not the case. How could you deal with that?
So all of this that we're doing is for a free field. Okay, mm-hmm. So we do not consider in any points interacting fields or even mm-hmm. self-interacting fields. That will change completely the methods of renormalization. Okay, mm-hmm. And yes, I agree with you. For interacting field, stress energy tensor wouldn't be expressed in such a simple form. And to be fair, I haven't read about renormalization in the case of interacting fields in curved spacetime. I know that there is literature about that, but I haven't dealt with it. So I know that it's a different matter, completely different matter.
Yeah, well, some possibilities would be to use your methods to work in interaction picture, for example, and in this way, your scalar field would obey the free field equations, no? And the point is, the interaction picture does not exist, as we always discussed formally. No? It exists formally, but perhaps it does not exist in fact. But in any case, the point is that in this case, I don't see the stress energy tensor being expressed like this. Perhaps you should use another prescription for the normalization in this case, or something more traditional, I don't know.
Yeah, for the interacting field case, I know that there are many shortcomings that appear which are not present in the free field case. And for example, even things which are very straightforward in flat space-time, and despite the fact that in curved space-time, renormalization is much more difficult even for a free field, but for the interacting field, more shortcomings appear. For example, even the definition of the time-ordered product becomes very difficult for the interacting field in curved space-time, which is something that does not happen here for the free field. So I mean, even to define the time-ordered product, which is something necessary in order to perform calculations in quantum field theory, it becomes very difficult for interaction field.
Okay. And after this, I would address something that you said. This is part of that ignorance I mentioned previously. You say in page 5 of your project that in general, the method can be applied in stationary and axis-symmetric spacetimes, for example, Kerr. Excuse me, let me read the first part of the paragraph. Let us consider a real scalar field phi of x with mass m and coupling psi to the richest scalar r, propagating on a space-time with metric g mu nu. No? So you set some very general situation or context. And then you say your method can be applied only in stationary and axis-symmetric spacetimes. I didn't catch the problem to apply your method to a general spacetime in principle. Is it related to some difficulty to solve the homogeneous equation for the field and find these functions, the L omega functions?
No, it's just that the main idea of the method is to decompose the counterterms in L, M, and omega modes. And this kind of decomposition require some kind of symmetry, right? Some kind of symmetry.
Yeah.
Right. So for general space-time, it's not, you can't do this kind of decomposition, right? So that's the.
I see.
That's the problem.
Okay. Now I understand. Okay. All right. And a final comment would be the following. In page 7 of your project, you say you you say textually after formula 2.6, but once again, I don't need you to put this explicitly in the screen. You say the result of the renormalization process, however, should be the, should be the same, both when using Christensen's counter terms or Hadamard regularization. For me, it's used to renormalization in flat space. This is not obvious at all. That the result of renormalization process should be the same. If you use different renormalization schemes, you arrive at different results. But in general, for the 2-point function, not for physical observables. The point is that perturbatively, these results, they differ in a term which is of the next order in perturbation theory. But they are not the same, you know.
Right.
This is another way to say that the 2-point functions evolves according to the renormalization group. They obey a non-homogeneous equation for non-homogeneous renormalization group equation. So for me, I mean, it's natural that if you renormalize in some way or renormalize in another way, you obtain two different results. These results can be related through the addition of finite counter terms in general. Yep. So if two results, you can take them to be the same between, entre aspas, você vai me entender, né? Two results are meant to be the same if they are related through the addition of finite counter terms. Yep. You know.
No, you're completely right. That's what I meant essentially. By this phrase, because actually it has been shown by Wald that any renormalization method in curved spacetime that satisfies some axioms that he proposes give the same result up to ambiguities. Of the kind that you explained, ambiguities that can be absorbed in the redefinitions of the constants in the Lagrangian, right? So it's essentially what you said. So for finite differences that can be absorbed. In the Lagrangian.
It's not a sin to obtain the same results, you know. In fact, it's of great practical value. But this is not mandatory. That's what I meant.
Sure. No, you're completely right.
So I would like to finish here and move to the next step. I don't know if it's standard that Mark would also make observations on our comments, me and Adrian's comments. But anyway. Thank you very much, Gabriel and Mark.
Thank you.
Once again.
Thank you very much for your participation, Tiao. No, I think Gabriel's, well, as far as I'm concerned, Gabriel's answers were good to the various questions. So I think we now move on to the last stage, which is where we all leave except for Adrian and Tiao, who will write a little form and report back on Gabriel's progress. So Thank you very much, everyone, again.
Might I just say while you're both here, so I do have some specific technical comments, one of which, for example, is that renormalization ambiguity is reflected in the fact that you don't have a logarithm, that you're taking the logarithm of something dimensionful.
Yeah.
And you need to add a length scale, a renormalization scale into the Green's function to make these things meaningful, and that leads to these ambiguities. So, but I think that the more sensible thing is that I just either scan my notes, or I think you've seen my writing. I type them up so that you can just sort of take those on board.
Okay,
but,
thank you.
But thank you very much both for the thesis and for the presentation and for answering our questions.
Thank you.
Thanks again, Adrian. Okay, so we leave, I think.
Okay.
Okay, bye-bye, people.
Thanks, Gabriel.
We'll stop sharing.
Yeah.
You stay, Adrian.
Yep, I will stay. Let me see. So,
Okay,
yes,
can I leave now?
Yes, I think. Oh, who is the host? Probably CBVF, is it?
Gabriel, obrigada. Marco, obrigada. Só aguardo, vocês podem sair da sala. Tião, eu vou finalizar lá e te aviso, aí vocês podem começar, tá?